Hello everyone, I'm Chinmay of 8th Sem ECE department from Sri Venkateswara College of Engineering. Today, my seminar presentation is on an intelligent self-sustained run slicing framework for diverse service provisioning in 5G beyond and 6G networks. And the contents for today's presentation is introduction, literature review, objectives, proposed methodology, expected outcomes, advantages and applications, conclusions and references. Introduction. The concurrent provisioning of heterogeneous vertical services calls for an extremely flexible, adaptive, and intelligent network architecture which directly contradicts today's one-size-fits-all network design paradigm. Therefore, in the design of 5G beyond and the sixth generation networks, new network design operation approaches have attracted research attention, including network slicing and artificial intelligence. Network slicing is a key technology to support the concurrent provisioning of heterogeneous quality of services in the fifth generation, that is 5G beyond, and the sixth generation, that is 6G networks. Run slicing is to satisfy specific QoS requirements of different services in a flexible, efficient manner. The fundamental concept of network slicing is to divide one physical network into multiple virtual networks referred to as network slices, coexisting over a common shared physical network substrate with the purpose of achieving different QoS provisions in each virtual network. Run slicing framework is hierarchically structured, which decomposes the run slicing control into three levels, that is, the network level slicing, network generation node B, that is the G node B level slicing, and the packet scheduling level slicing. At the network level, the network resources are assigned to each GNode B at a large time scale with coarse resource granularity. At the GNode B level, each GNode B adjusts the configuration of each slice in the cell at the large time scale. At the packet scheduling level, each GNode B allocates radio resource allocation among users in each network slice at a small time scale. Network slicing can be considered as a convergence of software-defined networking, that is SDN, with network functions virtualization, that is NFV. By creating the network control plane, SDN can provide a global view of network infrastructure and the capability of programmable network control. By combining SDN and NFV, the dimensionality of each network slice during network slicing can be customized to best fulfill the specific QoS requirements. With the proposed run slicing framework, the QoS performance of emerging services is expected to be dramatically enhanced. And the literature review is the first paper is evaluating the impact of delay constraints in network services for intelligent network slicing based on SKM model. This paper was released in 2021 by the author L. McVie X. Esselbach and J. R. Pinney in August 2021. In this paper, we analyze the impact of delay constraint on the performance of an online resource allocation algorithm based on an intelligent, efficient squatting and kicking model, that is SKM, proved in other words to be the most effective up to the present time yet. The next paper is the 660 Lego, a framework for 60 network slices. This paper gives the framework that enables the composition of new slices as a combination of single domain slices in a relatively easy technology independent manner. Next paper is a service oriented deployment policy of end to end network slicing based on complex network theory. This paper evaluates the performance of deployment policy. The paper proposes that extensive simulations have been conducted. The results have shown that the algorithm performed better in terms of resource efficiency and the acceptance ratio. Objectives. The first objective is to understand the concept of network slicing key technology. The next objective is to identify the plausible option for implementing the slicing concept at RAN level by the model network operator to respond to the needs of particles. The third objective is to utilize the learning approach to enable the transition from a model-based control to autonomic and self-learning run slicing control. The fourth objective is to implement the run slicing and the splitting, which is a new paradigm focusing on creating highly efficient performance, agnostic next generation and cellular networks. Methodology. The proposed architecture has two advantages. By using the NFV, different kinds of resources are virtualized from dedicated network infrastructures. Then a network slice can be defined as a proper collection of resources, thereby further increasing the flexibility. On the other hand, because of the centralized architecture and virtualization of network resources, AI enabled technologies can be conveniently implemented. The network resources are mapped to the multi-dimensional resource pool according to its capability and its ability. In the network resource pool, resources are further divided into three dimensions, that is communication, computing, and caching. A G-Node B defined by 3GPP refers to the next generation base station in the future networks, which accommodates the service requests inside its coverage area, that is one cell. As mentioned before, due to the limited radio resources, it is challenging to sufficiently provide orthogonal radio resources to each G-Node B in the multi-cell scenario. As a result, some G-Node Bs will share the same radio resources, but this comes at cost of intercell interference. To address this issue, we can assign the same set of radio resources to multiple cells separated by an enough distance, which can reduce the interference to an acceptable level. The STM controller hosting services entities in close physical proximity for users can ensure the low end-to-end response time of service provisioning. Furthermore, the set of GNODBs in the multiple cell scenario is directly connected and managed by the STM controller. The RAN slicing framework. This is the framework for the RAN slicing network level slicing control. In this, there is a network level slicing control. This is the large time scale coarse granularity, and this is the small time scale fine resource granularity. These are the slices for URLLC, slices for MMMTC, slices for EMBBB. Then this mobile data will be collected here, and this will be sent to the hierarchical RAN slicing control strategy. Here, the self-learning capability, transfer learning plus conventional AI algorithms. The network level control policy PIN can set computational and communication capacity to support the operation of GNOBs according to the dynamic of service traffics. The space domain granularity of network level control is the whole geographical scope of the multi-cell RAN scenario. By analyzing the network-wide observations of networks, example, the spatial distribution of the service traffic volume, uses distribution, and so on, the SDN controller can achieve global view of the whole network. The network level control decides the network resource assignment among GNode Bs, which includes the following: communication capacity at each GNode B, computation capacity at each GNode B. RAN slicing at GNode B level. The assigned network resources determined by the network level control policy PIN at the last time scale according to the GNode B level control policy PIG. Each GNode B will tune the configuration of slices in its serving cell based on the dynamics of services traffic in the cell. In order to improve the QoS performance of services, the GNode B level control is not directly involved in the real-time radio resources scheduling. The GNode B level control has two main functions: ensuring QoS requirements of slices, ensuring the performance isolation among the slices. The GNode B level control is very important in the proposed RAN slicing framework when current configuration of the network slice cannot fulfill the desired QoS requirements of services. The GNode B level control policy will tune the slice configuration to improve the QoS performance of services. RAN slicing at packet scheduling level. Based on the configuration determined by the GNode B level, according to the packet scheduling level control policy PIP, each GNode B executes the PRB allocation to users based on the instantaneous service request. The scheduling process operates at a time resolution given by the so-called TTI, which is the smallest time granularity in the system and currently is 1 millisecond in long-term evolution. Based on the QoS requirements of three considered services, that is MMTC, URLLC, and EMBB, we propose the following sets of network slices, that is the slice for the URLLC service, slice for the EMBB, slice for the MMTC. URLLC states that this slice should guarantee ultra high reliable and ultra low latency requirements of the URLLC service. Next, the EMBB. The EMBB users usually generate service requests to the access internet with high average data rate requirements. MMTC, this slice supports the exchange of large amounts of messages between the Internet of Things devices. Results. The proposed run slicing framework is hierarchically structured, which decomposes the run slicing control into three levels, that is, the network level slicing, next generation node B level slicing, and packet scheduling level slicing. At the network level, network resources are assigned to each GNOB at a large time scale with coarse resource granularity. At the GNOB level, each GNOB adjusts the configuration of each slice in the cell at the large time scale. At the packet scheduling level, each GNOD allocates radio resource allocation among users in each network slice at a small time scale. Furthermore, we utilize the transfer learning approach to enable the transition from a model-based control to automatic and self-learning run slicing control with the proposed run slicing framework. The QoS performance of emerging services is expected to be dramatically enhanced. The self-sustained RAN slicing framework can certainly play an important role in the 5G beyond and 6G networks. Advantages. A single network may be utilized to provide a variety of services dependent on the user's needs and use cases. According to the network slice, network operators can assign the appropriate quantity of resources. It also offers the possibility of selecting RAN functions in situations with multiple users and group of users, running multiple services in accordance with the objectives of the operator. It significantly enhances operational efficiency and speed to market for 5G network service delivery. The self-sustained RAN slicing framework can certainly play an important role in the 5G beyond and 6G networks. Applications. Fueling the mobile broadband slice that focuses on communication, entertainment, and the internet. It can also be applied in IoT sector to serve retail, manufacturing, industrial shipping, and mission critical IoT applications such as medical and infrastructure industries, among the several others. Automated lifecycle management of slice based services offered as a network as a service. Network functions virtualization. Conclusion. Network slicing is a promising direction in the meeting of the diverse QoS requirements of emerging applications. In this paper, we have presented the design of a self-sustained run slicing framework for current services provisioning. We have proposed a new intelligent run slicing framework with self-sustained capability. Although we have presented a preliminary study on the key challenges and solutions, much more studies are needed in order to bring them into practice. For instance, current related works mainly focuses on designing framework of network slicing and optimization of network control, but neglect to integrate network slicing with the new physical layer technologies such as the orthogonal time frequency space modulation, which is called as OTFS, non-orthogonal multiple access (NOMA), massive multiple input, multiple output, that is MIMO, meta surfaces, and deployment of unmanned aerial vehicles, that is UAVs. With these new physical layer technologies, the transmission latency of service requests can be further decreased due to the improved spectrum efficiency. Nevertheless, the self-sustained RAN slicing framework can certainly play an important role in the 5G beyond and the 6G networks. These are the references which I've referred for this presentation. Thank you.